Hi, I'm Ebru A. Yorgan, and my project is on the creation of a novel visualization tool and its application to analyzing RNA sequence data for atherosclerosis. So with the rapid growth of scientific data sets and visualization tools, it's important to be constantly making improvements and adding novel features in order to be able to extract the most amount of information that we can from our data sets. Currently, Matplotlib, which is a very widely used visualization library, can only map data to one color, and as you can see over here, that restricts how much information we can understand from our data. I created a novel feature, and with my novel feature, you can see how different correlations and groupings can be seen in the data, which can lead us to understand more about the world around us. My engineering question is trying to find a way of how we can understand high-dimensional data sets better, and I will be applying this tool to see which genes, demographics, or disease stages can impact atherosclerosis, which I'll talk more about later. So I conducted an extensive literature review on visualization techniques, the different libraries available, the code structure of the libraries, dimension reduction, and much more. And you can see an example usage of my end result over here. And I chose to work with Matplotlib, which is a very widely used visualization library used by over 5 million scientists because of its flexibility and backward compatibility. I set up the necessary software and began implementing my novel feature. So 2 lists of data will be passed in by the user, and for each data point in the list, it will be mapped to one color, and the other one will be mapped to another color, and then they will be combined together to get a resulting color like you can see over here. Bins can be created, which we'll talk more about later, and the function returns a list of colors which the user can then pass in to any Matplotlib visualization. Here we'll be using a scatter plot, but really anything could be used. And the legend image would also be returned in order to be able to customize the legend image, which is created by overlapping 2 color gradients like we saw before. My feature comes with 9 built-in color maps, as you can see here, which I created on my own. The user can customize almost every aspect about the legend, and we also accommodate for different types of color blindnesses in our built-in color options. If the user doesn't want to use these color options, they can also pass in their two custom HSV colors, or they can choose from one of many Matplotlib's one-dimensional color maps to be used on each axis. Sometimes the data may not be linearly distributed, which is why it's very important to be able to normalize the data before mapping it to a color. And many different normalization options are available, such as logarithmic, centered around a certain point, power relationships, such as x squared. And after the data is normalized, the legend is also labeled accordingly to reflect that normalization. The user can also chop up the data into bins, as you can see over here. This one creates discrete color regions, which makes it easier to understand the data, but also the number of bins and how data falls into different number of bins may imply something about the two variables' relationships. The user can choose to increase the saturation of the colors or the values of the colors, and you can see the difference of the two over here. So to apply this novel tool, I'll be applying it to analyzing a high-dimensional data set for atherosclerosis, which is a condition where artery walls get blocked because of fat buildup. Here you can see a fatty streak, we have fibrous plaques, and this can lead to many heart conditions. And a data set was obtained from the University of Virginia that has about 14,000 genes of about 50 patients. The fatty streak, fibrous plaque, fibrous cap, normal tissue percentages, as well as the binary pathology, which was assigned by a professional, as well as demographic information. And this data was reduced using UMAP. UMAP is a data reduction algorithm based on machine learning techniques, and it's important to reduce the dimensions because it's hard to visualize data with over 14,000 attributes, and UMAP works by creating a fuzzy symplecal complex and then extended radii around each point and mapping it to a lower dimension, as you can see over here. So after passing my data through UMAP, I visualized the different disease stages as well as demographic information, as you can see here, and the same image without bivariate view, and you can see different groupings of the fatty streak and the fibrous plaque combinations, and how as the diseased state progresses, you can see the gradients and groupings of the two disease stages over here. And we can also see how age might impact atherosclerosis, with likely higher ages might lead to a higher risk of development. And here we used our bins feature and categorical labels for the different ethnicity groups, and 41% of females were diagnosed, while only 35% of men were diagnosed. To move on to the genetics, 2 important genetics were identified through literature review and then further analyzed with this novel tool. So one of them is HLA-C, which is a protein that can cause inflammation, which might have impact on atherosclerosis. And here we observe this very interesting gradient, which might indicate its relationship to atherosclerosis development. But further analysis needs to be done to say more strong relationships about this HLA-C gene. And the same goes for the keratin 8 gene. It is a self-antigen, and it might, which has impacts on immune responses. And here we also show another very interesting gradient with the keratin 8 gene with the UMAP groupings of fibrous streak over here, but fibrous plaque and fibrous cap percentages were also seen to have similar impacts of the keratin 8 and HLA-C gene, and which will be further analyzed in the future. So to conclude, I created a publicly available tool which can be found at this link, and it offers options for data normalization, legend customization, and allows for much more information to be extracted from data that could previously was impossible to be seen. And then I applied this to analyze RNA data for atherosclerosis. I performed dimension reduction, and I identified keratin 8 and HLA-C genes to potentially have impact on atherosclerosis development. We saw demographic correlations and also how different stages of atherosclerosis can develop over time together. For the future, I'm hoping to improve my new feature, as this is part of an ongoing effort to improve data visualization. I could gather data for users and perform analysis to see how impactful my new tool is. I could perform tests and data analysis on the tool's performance independent of the user. I could collect more information about atherosclerosis, such as calculating p-value, studying more potentially important genes, etc., and also making more testing and improvements to the bivariate legend, as well as other useful contributions to Matplotlib to improve data visualization. Here are my references, and thank you so much for listening.